4 October 2022. Scientific background on the Nobel Prize in Physics 2022. For experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. The Nobel Committee for Physics. Entanglement between a microscopic and a macroscopic system, the latter symbolized by Schrödinger's unfortunate cat. The basic notion in the EPR thought experiment is that distant members of an entangled pair are measured using operators that do not commute. See Figure 1. In the original formulation, the position x and momentum p of moving particles satisfied x, p equals I h bar. The experiment was reformulated in 1951 by David Bohm, 4, who instead considered a pair of entangled spin 1/2 particles that can be measured by the operators SI, satisfying SI Sj equals I h bar epsilon ijk sk, where epsilon ijk is the fully antisymmetric Levi-Civita symbol. Figure 1. A schematic of an EPR experiment. Pairs of entangled particles are prepared in a singlet spin state and sent in opposite directions from a source. In the figure, the entangled pairs are shown to be connected with dashed red curves. The spin direction of each particle is, in this initial state, totally undetermined. At some distance from the source, one particle from each pair passes a measuring device operated by A, or Alice, shown by the green window, that measures the spin component in the z direction, blue arrows. After passing the measuring apparatus, the particle appears with quantized spin in the z direction, with either spin up, as shown in the figure, or with spin down. Due to the strict anti-correlation between the spin orientation of the particles in the pairs, at the same time as Alice's particle appears with spin up in the z direction, then B, or Bob's particle, will appear with spin down in the z direction. In this way, the measurement performed by Alice effectively acts as a measurement of the other particle, indicated by the dashed green window, even if no measuring device acts on this particle. The EPR paradox appears if Bob instead chooses to measure in the x direction, red arrows. It then looks like there are sharp values for the spin in perpendicular directions, in clear contradiction to quantum mechanics. In Bohm's version of the EPR experiment, a pair of spin 1/2 particles is created in an entangled singlet state belong minus Dre, where the spin wave function is of the so-called Bell type, 1 minus go, equals 1 over radical 2, up, down, minus down, up, 3. In an experimental configuration such as in Figure 1, A and B, or Alice and Bob, 1, can perform measurements of the spin components along the directions A hat and B hat respectively, where A hat equals B hat equals 1. Alice and Bob observe perfect anti-correlation if they measure in the same direction, A hat equals B hat. For arbitrary orientations, the probability of measuring opposite spin values is 1/2 1 plus A hat dot B hat. Note that the singlet state belong minus Dre is independent of which quantization axis is chosen for the spin. 1. Alice and Bob are the conventional names of the parties in various quantum information protocols. The conceptual puzzle presented by EPR is as follows. The components of the spin operators, measured by Alice or by Bob, do not commute. For example, for A vector equals ZZ and A vector equal XCOP, we have parentheses SZ, SX, parentheses, equals IHSY. According to quantum mechanics, one cannot simultaneously assign a sharp quantum number to non-commuting observables. But in this case, this seemingly leads to a contradiction, which is seen as follows. Assume that Alice measures SZ and gets the result 1/2. Then, from equation 3, it follows that if Bob were also to measure SZ, he would get minus 1/2 with 100% probability. This is true event by event. But Bob can choose instead to measure SX and get a definite answer plus 1/2 or minus 1/2. So it seems that both spin components have sharp values. It thus seems that we can assign sharp values to both spin components. Einstein, Podolsky, and Rosen concluded. From this follows that either 1. The quantum mechanical description of reality given by the wave function is not complete, or 2. When the operators corresponding to two physical quantities do not commute, the two quantities cannot have simultaneous reality. 2. Clearly, Einstein and his younger colleagues believed in the first alternative, although they acknowledged the logical possibility of the second. Indeed, one would not arrive at our conclusion if one insisted that two or more physical quantities can be regarded as simultaneous elements of reality only when they can be simultaneously measured or predicted. 3. This was indeed the position of Niels Bohr, and the debates between these luminaries of modern physics would form the understanding of quantum mechanics for generations of physicists that followed. Bell inequalities. Most working physicists, if they were interested in the issue, sided with Bohr, and especially so after John von Neumann presented a proof showing that it is impossible to complement quantum mechanics with hidden variables that would determine the outcome of any experiment. Still, some people kept pondering problems related to the foundations and interpretation of quantum mechanics. For example, in 1957, Hugh Everett proposed the many worlds interpretation of quantum mechanics 5 as an alternative to the then dominant Copenhagen interpretation. The latter comes in different variations, but the basic claim, following Bohr, is that there is a sharp distinction between the microscopic phenomena described by quantum mechanics and the macroscopic detectors used to study them, which are assumed to obey the laws of classical physics. The many worlds interpretation makes no such division, but instead purports that whenever a measurement takes place, a different world is created, and that there is no connection between the different worlds. In this interpretation, Schrödinger's cat would be alive in one world and dead in another. Yet another alternative to the Copenhagen interpretation was the Bohmian or pilot wave version of quantum mechanics 6. This is a fully deterministic theory that reproduces the results of non-relativistic quantum mechanics, but at the price of non-locality. Because the theories of Bohm and Everett did not make any experimentally testable predictions that differed from standard quantum mechanics, most physicists regarded these kinds of proposals as rather esoteric, and preferably only discussed during coffee breaks or in philosophy and history of science departments. This was the state of affairs in 1964, when John Bell published the paper on the Einstein-Podolsky-Rosen paradox. 2. Earlier in the paper, EPR defined element of physical reality as follows. If, without in any way disturbing a system, we can predict with certainty, that is, with probability equal to 1, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity.
Bell pointed out that von Neumann's proof was not correct. He gave the proof of this statement in a later publication, 8, and he also formulated the first Bell inequality, which was a spectacular theoretical discovery. Using a special version of the Bohmian EPR thought experiment, he showed mathematically that no theory based on local hidden variables would be able to reproduce all the results of quantum mechanics. With this mathematical illustration, Bell provided a proof of the assertions made by Bohr and Schrödinger, and thus showed that all attempts to construct a local realist model of quantum phenomena are doomed to fail. Bell used the words local and realist here in a technical sense. The former indicates the impossibility of instantaneous signaling, limited by the finite speed of light, and the latter means that the outcome of any experiment is fully determined by properties of the system, often referred to as hidden, that exist independently of any actual or potential measurement. Bell first derived an inequality for a certain correlation function that has to be obeyed by any local realist theory. And he then showed that for some experimental conditions, the predictions of quantum mechanics violate this inequality. The thought experiment considered by Bell is not suitable for experimental tests, simply because it makes assumptions about the detectors that cannot be justified for real equipment. This obstacle was removed in 1969 by John Clauser, Michael Horn, Abner Shimony, and Richard Holt, CHSH. They proposed a variation of the Bell inequality that was indeed possible to check by an experiment on entangled photons using existing technology. 9. Below, we first explain the CHSH inequality, then we describe the subsequent experiment performed by Stuart Friedman and Clauser. 11. The CHSH scenario shown in Figure 2 differs from the EPR thought experiment in that Alice can perform two different experiments that we denote by A1 and A2. Typically, the measurement of the spin in two different directions, A1 and A2. Similarly, Bob can measure B1 or B2. Assuming local realism, the measurement outcomes one would obtain for each individual quantum system are well defined, even if a measurement is not made. Quantum mechanics does not predict the results of the measurements, but they nevertheless should be considered as elements of reality in the EPR sense. Denoting the results of a potential measurement with A1, B2, etc., with the discrete outcomes A1 equals plus 1, etc., we have A1, B1 plus B2, plus A2, B1 minus B2, equals plus 2, since either B1 plus B2 equals plus 2, in which case B1 minus B2 equals 0, or vice versa, and both A1 and A2 take the values plus or minus 1. The experiment can now be repeated many times, and in each instance, Alice chooses to measure either A1 or A2, and Bob chooses to measure either B1 or B2. In a realist model, because the relation 4 holds for every individual measurement, we can obtain the correlations between the measurement outcomes simply by taking an ensemble average over the measurements. That is, EA1 B1 equals A1 B1, etc. We then arrive at the inequality. S equals modulus of EA1 B1 plus EA1 B2 plus EA2 B1 minus EA2 B2 less than 2, which holds for any realist theory. Figure 2. The source S produces pairs of entangled photons, sent in opposite directions. Each photon encounters a two-channel polarizer, whose orientation can be set by the Alice and Bob. Emerging signals from each channel are detected by single photon detector D+ and D-, and coincidences counted by the coincidence unit. The correlation EE of AB is equal to N++ minus N+- minus N- plus N- all over N++ plus N+- plus N- plus N-, where N++, N+-, N-, and N-, are the number of coincidence events recorded corresponding to the simultaneous detection at Alice's and Bob's detectors D+ and D+, D+ and D-, D- and D+ and D-, respectively. We can now compare this result with what is predicted by quantum theory. If the pair is in the state 1 over root 2, phi minus grand, given in equation 3, it is straightforward to show that EE of A1, B1 equals minus A1 dot B1, and the same holds true for the other combinations. It is now possible to see that one can choose the directions so that A1 dot B1 equals A1 dot B2 equals A2 dot B1 equals minus A2 dot B2 equals 1 over root 2, so S is equal to 2 root 2, which is in clear violation of the CHSH version of the Bell inequality. 5. The Friedman-Clauser experiment. The story might have stopped here. Some people said, well, this is really weird, but dismissed that thought because the status quo already held that quantum mechanics is strange, Schrödinger's cat is bizarre, and so on. And despite the bizarreness, it all seemed to work, so the inclination of the research community at the time was to just carry on using quantum mechanics. Indeed, initially very few people took notice of Bell's work. However, those few who did worried. Could it be that quantum mechanics does not always work? What about performing an experiment that tests quantum mechanics in one of those situations where it contradicts local realism? These were clearly the questions behind the CHSH work, and one of the authors, Clauser, set out to perform the experiment, together with the now deceased Friedman. Clauser had a background in molecular astrophysics from his PhD thesis, working with Pat Thaddeus as his advisor at Columbia University in the city of New York. As a PhD student, he had acquired an interest in the foundations of quantum mechanics. Thus, when he arrived at the University of California, Berkeley, UC Berkeley, to work as a postdoctoral researcher with Charles Townes in 1970, Clauser was prepared. He knew that Carl Kocher had built experimental equipment as part of his PhD thesis at UC Berkeley in 1967 to study the time correlation between pairs of photons originating from a common source, 10.
Clauser thought this experimental equipment could be used and improved to experimentally test the Bell-CH-SH inequality. The problem was that Townes had hired Clauser to work on radio astronomy and search for molecules in the interstellar medium, a research field that Townes had pioneered. Figure 3 shows the energy level diagram of calcium, which is the atom used by Kocher and his advisor Eugene Cummins, 10, to create pairs of photons, one at wavelength 5513 angstrom and one at 4227 angstrom. Energy level diagram for calcium, Kocher and Cummins, 10. The ground state is excited to the 6-1p1 state by a photon from a hydrogen arc lamp with a wavelength of 2275 angstrom. The initial state in the cascade is then populated by a transition 6-1p1 to 6-1s0. The parities of the initial and final atomic states are even, and therefore the photon state must have even parity. This means a plus sign is necessary in equation 3. Of course, the equation must be rewritten to take into account that it is now photons with helicities equal to +1 and not spin half particles. For a photon pair emitted in cascade in calcium, the two polarization states with zero total angular momentum are ++, both photon helicities positive, and -, both photon helicities negative. The photon state then becomes phi plus equals 1 over square root 2 plus minus. Here, plus and minus refer to the helicity quantum number. Positive helicity means that the spin angular momentum is in the direction of the linear momentum of the particle, while for negative helicity it is the opposite. From Kocher's PhD thesis, Polarization Correlation of Photons Emitted in an Atomic Cascade, Lawrence Berkeley National Laboratory, 1967. Because the two photons have a common origin, they can be shown to be entangled. The coincidence between Alice's and Bob's detection rates for antiparallel photons is R equals 1/2 cosquared phi,
where phi is the angle between the axes of the polarizers. In the original experiment, the polarizers were oriented at 0 degrees and 90 degrees with respect to each other, which means that a time correlation could be measured at 0 degrees, whereas no correlation was observed at an angle of 90 degrees. Kocher's PhD thesis clearly showed that he was aware of Bell's inequality, but with the angles he chose, he was not able to test the inequality. Kocher had already left UC Berkeley when Clauser arrived, but his experiment was still in the lab. Clauser was by now well aware that no previous experiment had tested the Bell-CH-SH inequality. He got Townes interested, and Townes made an agreement with both Clauser and Cummins. Clauser could work half-time on the Bell tests, and Cummins' PhD student at the time, Friedman, was allowed to work together with Clauser. Clauser and Friedman had identified the polarizers as the weak point in Kocher's experiment. The polarizers' inefficiency would make it prohibitively time-consuming to carry out the experiment at a number of different angles between the polarizers. The two researchers chose instead pile-of-plates polarizers, which have much better efficiency. It took 2 years for Friedman and Clauser to rebuild Kocher's experiment so that it could be used to test the Bell-CH-SH inequality, and about 200 hours to record the data. Figure 4, schematic diagram of the apparatus and associated electronics used by Friedman and Clauser, 11. The distance between the detectors was 5 meters. Figure 4 shows the modified experiment, and Figure 5 the experimental data. Friedman and Clauser 11 rewrote the inequality as delta R equals R times 220 degrees, R times 0 degrees, minus R times 67 degrees, R times 0 degrees, all delta minus 1/4 equals 0. Where r 22.5 degrees and r 67.5 degrees are the coincidence rates at the angles between the polarizer axes of 22.5 degrees and 67.5 degrees, respectively, and r0 is the coincidence rate with the polarizers removed, 11. The measurement gave delta equals 0.050 plus or minus 0.08, in clear violation of the inequality in equation 6. The measured values for RF phi over R0 at different angles phi are shown in figure 5. The curve is that calculated from quantum mechanics and not a fit to the data points. Figure 5. The experimentally measured ratio RF phi over R0 as a function of the angle phi between the axes of the polarizers. The solid line is not a fit to the data points, but the polarization correlation predicted by quantum mechanics. From Friedman's PhD thesis, Experimental Test of Local Hidden Variable Theories, Lawrence Berkeley National Laboratory, 1972. The aspect experiments. Like all theoretical results, Bell inequalities are derived under certain assumptions. One of these was of particular concern to Bell himself, the assumption that the two observers, Alice and Bob, make random choices of what to measure independent of each other. For this to be true, one must make sure that Alice cannot send a message to Bob about whether A1 or A2 is measured, which Bob receives before he decides to measure B1 or B2. In other words, Alice will not influence Bob's choices. Assuming that special relativity is correct, this locality condition amounts to making sure that such a message would have to travel with a speed greater than that of light. There are also some other assumptions that we shall briefly discuss in a later section. Alain Aspect was the first to design an experiment that avoided the locality loophole. In 1981 and 1982, together with collaborators Philippe Grangier, Gérard Roget, and Jean Dalibard, Aspect performed a series of experiments using improved techniques and novel instruments, 12 through 14. He established a violation of a Bell inequality with very high precision, tens of standard deviations, 13, as compared with the 6 standard deviations of the Friedmann-Clauser experiment, 11. More importantly, Aspect ensured the independence of Alice and Bob by using polarization settings that changed randomly during the time of flight of the photons between the detectors, 14.
In the first experiment, 2 laser systems were used to directly excite the 6-1s0 state by means of 2-photon absorption. This was much more effective than using a filtered hydrogen, deuterium arc lamp and populating the 6-1s0 state via the 6-1p1 to 6-1s0 transition, see Figure 3. In the next experiment, Aspect and collaborators used 2-channel polarizers in dichromatic measurements. This allowed them to obtain excellent statistics and the largest violation of Bell inequalities at the time, 13. However, it was the third experiment, 14, that garnered the most attention. Rotating the orientation of the polarizers was known to be impossible on a timescale comparable to the photon flight times. With a distance of 6 meters from the calcium photon source to each polarizer, this leaves no more than 20 nanoseconds, ns, to rotate the polarizers. In 1976, Aspect proposed an experiment, 15, in which acousto-optical devices could be used to switch the photons into 2 different branches of the apparatus on timescales shorter than the available 20 ns. See Figure 6. Group could test the inequality under strict local conditions, 16, with the observers separated by 400 meters and with a number of other technical improvements. Entanglement as a resource. The experiments of Clauser and Aspect opened the eyes of the physics community to the profound importance of entanglement, and they provided the tools to use distant but still entangled photons such as Bell pairs as a quantum resource. This resource has become central to the rapidly developing field of quantum information science. We now discuss some of the highlights of the development that has taken place in the 40 years that have passed since Aspect's first experiment. The examples refer both to fundamental discoveries in quantum physics and to results that are of direct relevance for practical applications. The no-cloning theorem, 17, says that no unitary transformation can produce a copy of an arbitrary quantum state while maintaining the original. To show this, assume that there exists a unitary cloning operator, U hat, that acts on two arbitrary states, psi1 and psi2 as U hat psi1 bow phi equals psi1 bow psi1 and U hat psi2 bow phi equals psi2 bow psi2. By using the linearity of the unitary operator, we find for the unknown quantum state psi equals alpha psi1 plus beta psi2 that U hat psi bow phi equals alpha psi1 bow psi1 plus beta psi2 bow psi2, but also equal 7 psi bow psi equals alpha psi1 plus beta psi2 bow alpha psi1 plus beta psi2. Since the results are different, we conclude that such a cloning operator does not exist. Clearly, the problem is that the right-hand sides of equation 7 are nonlinear in psi1 and psi2. Thus, quantum states cannot be copied. However, the possibility to teleport an arbitrary quantum state from one position to another remains so long as the original copy is destroyed. The first proposal for how to do this was given in 1993 by Bennett et al., 18, and the first experiments were performed in 1997 by the groups of Anton Zeilinger, 19, and Francesco De Martini, 20. We outline the general idea of teleportation protocols using a simple example. For a two-level system, there are 4 Bell states. In addition to hein psi plus ga, defined in equation 3, we also have hein phi plus ga equals 1 over the square root of 2 hein pa pla ga plus hein did de ga, and it is easy to show that these states are orthogonal and span the full Hilbert space for two two-level systems. To teleport an unknown state psi ga 1 from Alice to Bob, one first arranges for them to share one Bell pair, say hein phi minus ga, so the total state of A and B is hein bi ga 1 2 3 equals psi ga 1 bow phi minus ga 2 3.
Where Alice possesses the states 1 and 2, Bob possesses state 3, and 2 and 3 form the shared Bell state. With a bit of algebra, one can rewrite this combined state in terms of the 4 Bell states. 1/2 times, open parentheses, the first Bell state multiplied with the operator V4, plus the second Bell state multiplied with the operator V4, plus the third Bell state multiplied with the operator V2, plus the fourth Bell state multiplied with the operator V1, where the operators Vi all have the property that Vi squared equals 1. Next, Alice performs a joint measurement on the states 1 and 2 with an operator that projects them into one of the Bell states, say Bob phi minus 1 2. So the total state becomes partial 1 2 3 4 towards Bell state 1 2 multiplied with the operator V4 on his state 3. Finally, Alice sends a classical 2-bit message to Bob that he should apply V4 on his state, and in doing so, he will recover Bob phi 3, since V4 squared equals 1. A closely related phenomenon is that of entanglement swapping, which, as we shall see below, is of practical importance for quantum communication. In a swapping event, one source emits the photons 1 and 2 in a Bell state, and another source emits the photons 3 and 4 in another Bell state. Photons 1 and 4 are received by Alice and Bob, respectively, while 2 and 3 are arranged to arrive simultaneously at C to Cecilia, as illustrated in Figure 7. Thus, using the same notation as above, the original state can be written as box partial 1, 2, 3, 4 equals Bell state 1, 2 multiplied with Bell state 3, 4. And by manipulations, similar to the case of the teleportation example, we can rewrite it as box partial 1, 2, 3, 4 equals 1/2 times, open parentheses, the first Bell state multiplied with the next Bell state, plus the second Bell state multiplied with the next Bell state, plus the third Bell state multiplied with the next Bell state, plus the fourth Bell state multiplied with the next Bell state. Figure 7. Schematic setup for an entanglement swapping experiment, 22. The two sources of entangled pairs of photons were in this case by parametric downconversion in nonlinear crystal, which is a much more efficient source of entangled photons than can be obtained from an atomic cascade. The entangler is in the text called C for Cecilia.
In the next step, Cecilia makes a joint measurement projecting on one of the 4 Bell states of 2 and 3, and as in the teleportation case, this measurement can now be chosen to be projected on a particular Bell state, say by psi minus 2, 3, as by psi 1, 2, 3, 4 projects minus by psi minus 1, 4 cross by psi minus 2, 3. Thus, although they were never close to each other, photons 1 and 4 are now entangled, and Alice and Bob share a Bell pair. The first discussion of this possibility was by Bennett et al. 18, and later in the same year, Marek Zukowski, Zeilinger, Horn, and Arthur Eckert coined the term entanglement swapping and showed how, via an initiating event, it could be used to decide when an entangled pair has been produced, 21. The first experiment to demonstrate this was published in 1998 by Jian-Wei Pan, Dick Baumeister, Harald Weinfurter, and Zeilinger, 22. The problem facing Zeilinger's group was how to implement the simple scenario shown in Figure 7 in a real experiment. Figure 8 shows the experimental setup and how a Bell measurement on photons 2 and 3 leads to entanglement of photons 1 and 4. The details of the experiment are explained in the caption of Figure 8, and the data shown in Figure 9 clearly demonstrate the polarization correlation and hence entanglement between photons 1 and 4. Figure 8. A UV pulse passing through a BBO crystal, BBO204, creates down-converted pairs of entangled photons 1 and 2. After a reflection, during its second passage through the crystal, a second pair, 3 and 4, of entangled photons is created. Photons 2 and 3 are directed to the beam splitter in the upper gray box. When a coincidence between photons 2 and 3 is registered, they are projected into the by psi minus 2, 3 state. This projection results in photons 1 and 4 becoming entangled. To demonstrate entanglement between photons 1 and 4, coincidences between detectors D4 and D1 plus and D4 and D1 minus are measured from Ref 22. Figure 9. Fourfold coincidences resulting from twofold coincidences D1 plus D4 and D1 minus D4 as a function of polarizer angle theta at D4. The two complementary sine curves show that photons 1 and 4 are entangled. From Ref 22. Quantum repeaters and quantum networks. An important goal of quantum technology is to be able to distribute entanglement over very large distances in order to communicate quantum information. The simplest means is to use an optical fiber, but the problem is that light is attenuated, so that on average every second photon is lost in a 10-kilometer-long fiber. In classical communication networks, the problem is solved by placing amplifiers along the fiber links.
Because of the no-cloning theorem, this is not possible in the quantum case, since classical amplifiers work by effectively making many copies of the original message. There are two ways to deal with this problem of loss. The simplest solution is to avoid the loss by sending signals through space using satellites. Since the effective depth of the atmosphere is about 10 kilometers and the loss in empty space is very small, one can establish entanglement over very large distances. This approach was spearheaded by a team led by Jianwei Pan, using the first quantum communication satellite, 2324 Messius, launched by China in 2016. Pan and colleagues demonstrated satellite-based distribution of entangled photon pairs between two locations, separated by 1,203 kilometers on Earth, through two satellite-to-ground downlinks, with a total length varying from 1,600 to 2,400 kilometers. They observed survival of two-photon entanglement and a violation of the Bell inequality by 2.37 plus or minus 0.09. Later, in collaboration with Zeilinger's group, they used the same satellite as a trusted relay to distribute a secure key between Beijing and Vienna. With a higher orbit satellite, which is under construction, it will be possible to directly distribute entangled photon pairs over 10,000 kilometers. The second approach to long-distance quantum communication uses quantum repeaters, which are devices based on entanglement swapping. Repeaters can break a communication line into shorter parts and enable the use of swapping to transfer the entanglement from Alice to Bob through several nodes. In addition to an efficient swapping protocol, one also needs good quantum memory, since Alice must store her state until it is entangled with Bob's, which it will be, after a number of swapping events. Combining these technologies could lead to the construction of a global quantum network, wherein distant nodes are connected by satellite, and then to regional nodes by optical fibers and quantum repeaters.
Entanglement between many particles. Thus far, we have only discussed Bell pairs, or entangled states of two particles. However, entanglement is a basic property of any interacting quantum state. An important problem in condensed matter physics is to classify the possible ground states of systems with many electrons, and, in particular, those of relevance for the recently discovered topological materials. A classification in terms of entanglement could provide a sharp distinction between various phases of matter, and a quantity called entanglement entropy could be used to identify many of them. Controlled entanglement is by no means restricted to polarization states of photons. Enormous effort has gone into establishing other good two-level systems that can be used in quantum technology, and in particular in quantum computing. Examples are spins in trapped atoms or ions, certain color centers in crystals such as diamond, and charge or flux states in superconducting electric circuits. In the last example, the two-level system arises as a collective effect in the motion of a macroscopically large number of electrons. To better understand and classify different types of entanglement and to find good measures of entanglement when more than two parties are involved are important tasks for both theoretical physicists and mathematicians, and there are many open questions. We discuss here just one example where entanglement between three particles resulted in a spectacular new insight. In 1989, Daniel Greenberger, Horn, and Zeilinger treated four-particle states, 25, and a year later, together with Shimony, a three-photon state. 1 over square root 2 times curly by up, 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 plus by down, down, down. Here, as above, we use the spin notation for the polarization directions. By measuring Sx or Sy in different combinations for the three particles, one can establish certain perfect correlations, meaning that knowing the result of the measurements of two particles, the result for the third can be inferred with certainty. This is akin to the absolute correlations in the original EPR experiment, with both detectors having the same polarization. Such absolute EPR correlations are easily explained by local hidden variables, but the absolute correlations in the GHZ state, which follow from the quantum description, defy any such explanation. Thus, it is enough to experimentally establish these correlations to exclude local realism, and there is no need to evoke any inequality.
A very clear and simple proof of this surprising result was given by Merman, 27. In 1999, Zeilinger's group managed to produce the 3-photon GHZ state, 28, and a year later, they showed that it violated a Bell inequality, as predicted by the theory, 29. Quantum cryptography and recent developments based on Bell tests. Today, quantum technology refers to a very broad range of research and development. As an illustration, we mention that the EU-financed quantum technology flagship, 30, lists 4 main areas: quantum computing, quantum simulation, quantum communication, and quantum metrology and sensing. In all of these areas, quantum entanglement plays a fundamental role. This is an inappropriate venue to survey this vast landscape of innovative research. Rather, we briefly discuss quantum key distribution, since it is closely connected to the developments we have covered so far. The only known way to send messages that are guaranteed to be safe from eavesdropping is to have a shared and secret cryptographic key that is only used once. The problem is how to distribute a key shared by Alice and Bob in a secure way, and here is where quantum key distribution, QKD, comes in. In 1991, Arthur Eckert proposed an entanglement-based QKD protocol 31.4. In brief, it works as follows. A and B share a Bell pair that is emitted from an independent source. Then A measures the spin in one of the 3 directions, AI, I equals 1, 2, 3, which is picked randomly, and B does the same in the directions BI. After the measurements, Alice and Bob openly broadcast which spin component has been measured and divide the events in 2 groups. The first group contains events in which the same direction was chosen, and the second in which they were different. The next step is to openly reveal the results of the measurements in the second group. This data can then be used to construct a variable S, as in EQ4, and perform a Bell test. If this is as expected from quantum theory, that is, if the correlations are violating a Bell inequality, then the events in the first group, which are totally anti-correlated, can be used to create a secret key. In 2006, the Zeilinger group used this scheme and an optical free space link to establish a secure key between the 2 Canary Islands, La Palma and Tenerife, that are separated by 144 kilometers, 32. The experimenters used polarization entangled photon pairs, and in a test of the CHS inequality, they obtained S equals 2.508 plus or minus 0.037, demonstrating violation of the local realistic limit by more than 13 standard deviations. The above example demonstrates that violating Bell inequalities are not just a matter of quantum mechanical ontology, but can be put to practical use. In this context, we briefly return to the different loopholes in Clauser's original experiment. We already discussed the locality loophole in relation to Aspect's experiment. This was the loophole that was stressed by Bell, and of the other loopholes, 33, the one considered to be the most important is the detection loophole. This arises because no detector has 100% efficiency. Some photons are invariably lost, and if nature is cruel, these photons might conspire to fake a violation of a Bell inequality. This can be avoided by having sufficiently good photon detectors, but the detection loophole was first closed in an experiment using trapped ions, 34, and later in other systems. However, in these experiments, one could not close the locality loophole, and it was only in the years 2015 to 17 that 4 groups, one of them led by Zeilinger, managed to simultaneously close both the locality and detection loopholes, 35 through 38. The main importance of these results is not to once again confirm that quantum mechanics is correct, but rather to enable even more secure QKD protocols. Since these depend on Bell tests, the issue here is not whether nature conspires to violate Bell inequalities, but whether the evil eavesdropper Eve does. In 2022, 3 groups used loophole-free Bell tests to experimentally realize device-independent QKD protocols 39 through 41. This means that the key is secure even if Eve has access to the quantum hardware that runs the distribution. For details, we refer the reader to the original papers. Conclusions. The founding fathers of quantum mechanics were well aware of its potentially revolutionary physical and philosophical implications and held very different and sometimes bluntly contradictory views on the subject. By proving that quantum mechanics makes predictions that cannot be reproduced by any conceivable theory based on local hidden variables, John Bell transformed philosophy into empirical science, forever changing the field. The transformation did not expunge controversy. Indeed, the overwhelming empirical evidence in the realms of atomic and optical physics was, to most practitioners, confirmation of the potent predictive power of quantum mechanics. Thus, to them, the experiments of Classer and Aspect came as no surprise.
Others saw them as fundamental discoveries about the nature of physical reality, providing an ultimate verification of quantum mechanics in a regime that is far removed from classical laws and reasoning. 4. The first QKD protocol, proposed by Bennett and Broussard in 1984, in Advances in Cryptology, Proceedings of Crypto 84, August 1984, Springer-Vallick, New York, pp. 475-480, did not utilize entangled pairs. This year's Nobel Prize is for experimental work. Apart from the disparities in philosophical interpretation, the early Bell experiments drove the development of what is often referred to as the second quantum revolution. Two of this year's laureates, John Clauser and Alain Aspect, are honored for work that initiated a new era, opening the eyes of the physics community to the importance of entanglement and providing techniques for creating, processing, and measuring Bell pairs in ever more complex and mind-boggling scenarios. The experimental work of the third laureate, Anton Zeilinger, stands out for its innovative use of entanglement and Bell pairs, both in curiosity-driven fundamental research and in applications such as quantum cryptography. References: 1. E. Schrödinger, Mathematical Proceedings of the Cambridge Philosophical Society, 31, 555, 1935. 2. E. A. Hyleros, Z Physics 48, 469, 1928. 3. A. Einstein, B. Podolsky, and N. Rosen, Phys. Rev. 47, 777, 1935. 4. D. Bohm, Quantum Theory, Prentice Hall, Inglewood Cliffs, N.J., 1951. 5. H. Everett, Rev. Mod. Phys. 29, 454, 1957. 6. D. Bohm, Phys. Rev. 85, 166, 1952, Ibid. 85, 180, 1952. 7. J. S. Bell, Physics 1, 195, 1964. 8. J. S. Bell, Rev. Mod. Phys. 38, 447, 1966. 9. J. F. Clauser, M. A. Horn, A. Shimony, and R. A. Holt, Phys. Rev. Let. 23, 880, 1969. 10. C. A. Kocher and E. D. Cummins, Phys. Rev. Let. 18, 575, 1967. 11. S. J. Friedman and J. F. Clauser, Phys. Rev. Let. 28, 938, 1972. 12. A. Aspect, P. Granger and G. Roger, Phys. Rev. Let. 47, 460, 1981. 13. A. Aspect, P. Granger and G. Roger, Phys. Rev. Let. 49, 91, 1982. 14. A. Aspect, J. Dalibard and G. Roger, Phys. Rev. Let. 49, 1804, 1982. 15. A. Aspect, Phys. Rev. D. 14, 1944, 1976. 16. G. Wyness, T. Genowine, C. Simon, H. Weinfurter, and A. Zeilinger, Phys. Rev. Let. 81, 5039, 1998. 17. W. K. Wooters and W. H. Zurich, Nature 299, 802, 1982. D. Dykes, Phys. Let. A. 92, 271, 1982. 18. C. H. Bennett, G. Brassard, C. Crepeo, R. Joza, A. Paris, and W. K. Wooters, Phys. Rev. Let. 70, 1895. 19. D. Baumeister, J. W. Pan, K. Mattel, M. Ebel, H. Weinfurter, and A. Zeilinger, Nature 390, 575. 20.
D. Boschi, S. Bronza, F. De Martini, L. Hardy, and S. Popescu, Phys. Rev. Let. 80, 1121, 1998. 21. M. Zukowski, A. Zeilinger, M. A. Horn, and A. K. Eckert, Phys. Rev. Let. 71, 4287, 1993. 22. J. W. Pan, D. Baumeister, H. Weinfurter, and A. Zeilinger, Phys. Rev. Let. 80, 3891, 1998.
23. S. K. Liu, W. Q. Chai, W. Y. Liu, L. Zhang, Y. Li, J. G. Ren, J. Yin, Q. Shen, Y. Cao, Z. P. Li, F. Z. Li, X. W. Chen, L. H. Sun, J. J. Jia, J. C. Wu, X. J. Zheng, J. F. Wang, Y. M. Huang, Q. Wang, Y. L. Zhou, L. Deng, T. Shi, L. Ma, T. Hu, Q. Zheng, Y. A. Chen, N. L. Liu, X. B. Wang, Z. C. Zhu, C. Y. Liu, R. Shu, C. Z. Peng, J. Y. Wang, and J. W. Pan. Nature 54943, 2017. 24. J. G. Ren, P. Hu, H. L. Yang, L. Zhang, S. K. Liu, J. Yin, W. Y. Liu, W. Q. Chai, M. Yang, L. Li, K. X. Yang, X. Han, Y. Q. Yao, J. Li, H. Y. Wu, S. Wan, L. Liu, D. Q. Liu, Ya. Wu, Z. P. Ha, P. Shang, C. Go, R. H. Zheng, K. T. Zhu, Z. C. Zhu, N. L. Liu, C. Y. Liu, R. Shu, Ya. A. Chen, C. Z. Peng, J. Y. Wang, and J. W. Pan. Nature 54970, 2017. 25. D. M. Greenberger, M. A. Horn, and A. Zeilinger, Going Beyond Bell's Theorem, in Bell's Theorem, Quantum Theory and Conceptions of the Universe, edited by M. Kafatos, Kluwer, Dordrecht, 1989, pp. 69-72. 26. D. M. Greenberger, M. A. Horn, A. Shimoni, and A. Zeilinger, A. M. J. Phys. 58 1131, 1990. 27. D. Merman, A. M. J. Phys. 58 731, 1990. 28. D. Baumeister, J. W. Pun, M. Daniel, H. Weinfurter, and A. Zeilinger, Phys. Rev. Let. 82 1345. 29. J. W. Pun, D. Baumeister, M. Daniel, H. Weinfurter, and A. Zeilinger, Nature 405151. 30. European Commission, Quantum Technologies Flagship, http://digital-strategy.eu.en/policies/quantum-technologies-flagship, http://digital-strategy.eu.en/policies/quantum-technologies-flagship, 2022-09-27. 31. A. K. Eckert, Phys. Rev. Let. 67661, 1990. 32. R. Urson, F. Tiefenbacher, T. Schmidt-Manderbach, H. Weyer, T. Scheidel, M. Lindenthal, B. Blaunensteiner, T. Genowine, J. Perbiguis, P. Trojic, B. Omer, M. First, M. Meyenberg, J. Rarity, Z. Sodonic, C. Barbieri, H. Weinfurter,
and A. Zeilinger, Nature Physics, 3, 481. 33. N. Brunner, D. Cavalcanti, S. Peronio, V. Scarani, and S. Wenner. Review Mod Phys. 86 419 2014. Erratum Ib. 86 839 2014. 34. M. A. Rowe, D. Kilpisky, V. Meyer, C. A. Sackett, W. M. Itano, C. Monroe, and D. J. Wineland, Nature, 409 791. 35. B. Henson, H. Bernian, A. E. Dreo, A. Reiserer, N. Cal, M. S. Bloch, J. Ruttenberg, R. F. L. Vermeulen, R. N. Schouten, C. Abelin, W. A. Amaya, V. Pruneri, M. W. Mitchell, M. Markham, D. J. Twitchen, D. L. Kos, S. Wenner, T. H. Taminio, and R. Hansen, Nature, 526 682. 36. M. Justina, M. A. M. Verstagog, S. Wengerovsky, J. Hansteiner, A. Hofreiner, K. Phelan, F. Steinlechner, J. Koffler, J. A. Larson, C. Abelin, W. Amaya, V. Pruneri, M. W. Mitchell, J. Bayer, T. Gerritz, A. E. Lita, L. K. Schalm, S. W. Nam, T. Scheidel, R. Urson, B. Whitman, and A. Zeilinger. Phys. Rev. Let. 15250401. 25. 37. L. K. Schalm, E. Meyer Scott, B. G. Christensen, P. Bierhorst, M. A. Wayne, M. J. Stevens, T. Gerritz, S. Glancy, D. R. Hamill, M. S. Allman, K. J. Coakley, S. D. Dyer, C. Hodge, A. E. Lita, V. B. Verma, C. Lambraco, E. Tortorici, A. L. Migdal, Ya Zhang, D. R. Kumar, W. H. Farr, F. Marsili, M. D. Shaw, J. A. Stern, C. Abelin, W. A. Amaya, V. Pruneri, T. Genuine, M. W. Mitchell, P. G. Quat, J. C. Bienfeng, R. P. Mirren, E. Kill, and S. W. Nam. Phys. Rev. Let. 15250402. 38. W. Rosenfeld, D. Burchardot, R. Garthoff, K. Redeker, N. Ortegel, M. Rau, and H. Weinfurter. Phys. Rev. Let. 119010402.
39. D. P. Nadlinger, P. Dermota, B. C. Nickel, G. Araneda, D. Main, R. Srinivas, D. M. Lucas, C. J. Balance, K. Ivanov, E. Y. Z. Tan, P. Sikotsky, R. L. Urbank, R. Renner, N. Sangward, and J. D. Bonkal, Nature 607 682 2022. 40. W. Zhang, T. Van Lent, K. Redeker, R. Garthoff, R. Schwonek, F. Furtick, S. Eppelt, W. Rosenfeld, V. Scarani, C. C. W. Lim, and Harold Weinfurter, Nature 607 687 2022. 41. W. W. Z. Liu, Y. Z. Zheng, Yi. Z. Zhen, M. H. Li, Y. Liu, J. Fan, F. Su, Q. Zhang, and J. W. Pon. Phys. Rev. Let. 129 050502.